going to begin this video by re-emphasizing what we stated at the end of the last video. That was that the rate law corresponds, the rate law for a reaction, which tells you how the speed of the reaction corresponds to concentrations of reactants. It does not correspond to the overall balanced equation for the reaction. It corresponds rather to the left side, the reactant side of the slow step in the mechanism for that reaction. So this mechanism shows that the slow step has NO2 plus NO2, which means two NO2s, which is where NO2 ends up, which is how NO2 ends up in our rate law, and it ends up with that coefficient as its exponent. Remember, the slowest step determines how fast the reaction runs because it's the one that takes the longest to run. So you could never expect to complete the reaction from start to finish, starting with all the reactants and ending with all the products. You can never expect it to run it through once any faster than you can run the slowest step in the reaction mechanism. So you can see for this example why we must have NO2 squared in the rate law. Also, I should point out the absence of carbon monoxide. You can clearly see that it is a reactant. And I said at the end of the last video, yes, carbon monoxide must be present for the reaction to run, but it doesn't determine how fast the reaction runs. You could triple it, quintuple it, put 10 times as much of it in there, it wouldn't speed up the reaction. But you go messing with the NO2 concentration, you're going to change the rate of the reaction. So carbon monoxide, you could say, well, it's a reactant, it should be in the rate law. Okay, if you want to, you could put brackets here and put CO in there and put a 0 for its exponent, and anything to the 0th power is 1, and it would kind of just disappear anyway. So we're going to talk about an experimental method. Since you can't look at the overall balanced equation and figure out the rate law from just looking at that, you have to go experiment until you can figure out something about the reaction mechanism to try to determine the rate law. Well, the method of initial rates is one experimental method for figuring out the rate law for a reaction. That's what its purpose is to determine the rate law for the reaction. And the way it's run practically is the reaction is initiated by combining the reactants, and then right away the rate is taken. The rate has to be checked right away because we don't want products building up, because when products build up, they could react with each other to remake reactants, and if reactants are being remade, then the concentration of reactants doesn't seem to be going down as fast. And so we try to get a snapshot of the rate of the reaction early on in the reaction when products is not built up. The way we do it also practically is by changing up concentrations of various reactants. We might hold concentrations of one constant and change the other, and then hold the concentrations of the other constant and change the concentrations of the one. So here's an example. Let's take, for example, the overall balanced equation for a reaction that is 2A plus B makes C plus 3D. And let's say that we're starting out with no products and only concentrations of A and B being the same at 2.5 molar. Now this is a graph where we're going to see the molar concentration at any time in real time, and then we're going to show the time at which we know that concentration on the x-axis. So if you were to run this like I did in some of my research as a graduate student, we had a readout on one of our spectrophotometers that showed you what the concentrations were in real time with a plot just like this. Here's what you would have seen if you could monitor simultaneously for A and B and C and D, which you can't do practically, but this is what you would see, and I've made the different colors here in the legend for the traces so you can see what we're talking about. In real time, you would see something like this. So we see curves, and then we see it flattening out. We'll explain what that means. Okay, why are the red trace and the blue trace sloping downward? Why do they have negative slopes? It's because they represent reactants, A and B. And A and B are being consumed. As the reaction runs, they're getting used up. being turned into products, right? So their concentration should be decreasing over time, and so their slopes are negative. Now, why are the slopes of the purple line and the green line positive? It's because they represent the concentrations of products, the change in concentration of products over time. So these slopes are positive because the products are being formed as the reaction runs. Why did the slope suddenly flatten out to 0? It's because we ran out of reactant A. Notice it was being used up twice as fast as reactant B. So when it ran out, it shut off the reaction. Now, A may or may not be a factor in the rate law. It may or may not determine how fast the reaction runs, but the reaction definitely can't run without A. So when A ran out, the reaction stopped. Okay, in real life you wouldn't see such sharp transitions, so it would be smoothed out more like this. So how do we take our measurements? I used to have a printout of this graph after it was done, and I would go try to figure out the slope early on. And so I've drawn a brown line here using, so this is like using a straight edge on a paper printout. This brown line lines up with the slope early on the blue trace. So we're talking about the rate of reaction for A. Well, what is rate of reaction? It's change in concentration of A over change in time. A rate is always a change in something over time. And so concentration of A is changing as time changes, and that's concentration is on the y, time is on the x. So this is the rise over the run. That's why we're saying the rate of reaction is the slope of this plot. And you can see we got final concentration of A, or initial, divided by final time over initial. Final concentration of A minus initial concentration of A divided by final time over initial time. We could do the same thing for B. Again, we're trying to make our slope of our line match the slope early on before products have built up, because this is the method of initial rates. Here you have the same thing for C and the same thing for D. So you'd say, well, you just showed me 4 different slopes. How are we supposed to report one value? What if lab A was monitoring concentration of B, and lab B was monitoring concentration of A, and lab C was monitoring concentration of C, but lab D was monitoring concentration of D? They would all be measuring this, trying to determine the rate of the same reaction, possibly even under the same conditions, and yet they'd be reporting different values. Well, to make sure that we always report the same values, we do this process of normalization. So I show you at the bottom how that works. If it's a reactant, we already pointed out reactant slopes end up being negative, so we put a negative out front. We put a negative out front of the slope for reactants. We don't put a negative for the slope for products because they're being formed, so their slopes are positive. Then notice that this 2, this 1, this 1, this 3, those all correspond to these coefficients from the balanced equation. And so since A gets used up twice as fast as B, if I'll just divide A's change in concentration by 2, I'll end up with the same value as I would for B, right? And since D is being formed 3 times as fast as C, if I'll divide the rate of change of D by 3, I'll end up with the rate of change of C. So that's the normalizing process. Okay, practically we can't monitor all 4 reactants and products at the same time. I don't know of any method to do it practically, so we usually are just monitoring just one. So let's assume that we're monitoring just the concentration of B as time goes by. So we set up a reaction, and then we have a way, like maybe with a spectrophotometer, to monitor for it. So here we go. We're running this reaction with A and B starting out at 2.5 molar, and of course there's no C and no D. And so we're just monitoring B, and here we go. So practically, how would we go figure out what the initial rate was? Well, we'd go get our straight line, line it up to the slope early on in that plot, and then I've used my X and Y intercepts here to get my rise over my run, and I found my molarity there. I've switched now, and we're talking about a second experiment. We're changing something up. We held A still at 2.5 molar initially, but our initial concentration of B we've changed to 1.25 molar, and we're still monitoring for the concentration of B as time goes by. And so if we watched in real time, we'd see this. I don't know if it felt slower to you, but it was slower. And so there's the, using the x and y intercepts, there's the rise over the run, there's the slope initially. And so that would be our rate, our initial rate under these conditions of 2.5 molar initial concentration of A and 1.25 molar initial concentration of B. So then we, as I said, we keep changing concentrations to, and in real life we'd have to do, you know, each of these that I've just described in triplicate just to get a good average. But I'm idealizing here and saying, oh, we ran it perfectly the first time. Okay, so now what we're doing is we put B back to its original concentration of 2.5 molar. We're starting off the reaction that way, and with A at a concentration half as much as it had been before. So we've flipped it from last time, from the second trial. And we run that, and of course A runs out really fast because it's getting used up twice as fast as B, so we flatten out sooner. So we go check our rate, and here's again using X and Y intercepts, we figure out our rate under those conditions of 1.25 molar A and 2.5 molar B initially. Compiling all that data into a helpful chart, here's our experimental data from trial 1, 2, and 3. Now we're going to do the math to try to determine our rate law out of this. So I'm going to start by comparing data from trials 1 and 2. Now notice in trials 1 and 2, A was held constant, but B was cut by half in the second trial as compared to what it was in the first trial. I'm going to notice that the numbers are bigger in trial 1. So I would put my information for 1 on top of my information for 2. What have I done here? I've taken a regular generic form of a rate law, which has rate on one side. It's got the rate constant K times the concentration of one of the reactants raised to an exponent times concentration of B raised to an exponent. And I've put a rate law like that, one over the other, made a fraction out of them. Okay, so, and again, I wanted to pick the one with the bigger values to be on top. So that's why I chose rate 1 to go on top of rate 2. If rate 2 had had bigger numbers, I would have put it on top. Okay, plugging in what we know. Here are the rates from experiments 1 and 2, trials 1 and 2. Here's the concentration of A, trials 1 and 2, B, trials 1 and 2. And notice we've got some unknowns, which is why we're doing this math. But the nice thing about having the concentration of A be the same in trials 1 and 2 is that they cancel out. And also, the rate constant K, as long as we've run these trials at the same temperature, the rate constant K is a constant, and therefore it would cancel. So this leaves us with 2.5 over 1.25 to the Y, which is 2.5 divided by 1.25 is 2. So we end up with this when we do some math. Now we have to solve for Y, which is our whole purpose here. We're trying to find the exponent on B in our rate law. So the natural log can be used to solve for these exponents, and here's a rearrangement following the rules of exponents, that the exponent can be made a coefficient out in front of the natural log there. And so rearranging, we solve for Y, and we get 1.99. Now I want you to understand that at our level we expect the coefficients, we expect the exponents to always come out to whole numbers. Later on, when you get more sophisticated in higher level chemistry studies, you may end up with some non-whole number exponents in your rate laws. But for now, we always expect them to be whole numbers. So the fact that it came out to 1.99, we're going to chalk up to some kind of experimental error, and we're going to round it off to 2. Okay, so what have we figured out so far? We figured out that in the rate law, which is this equation like this, concentration of B raised to the second power affects the rate. Now we don't know about A yet, and we don't know the K, so we're going to go find X next. So what 2 trials do we want to pick? Well, we want to pick trials where, ideally, where B is held constant and where A is changing. So that would force us to use trials 1 and 3. Now, hypothetically, if we had no trials where A was held constant, where B was held constant and A was changing, if we had no such thing, at this point we would be okay because we already know the value for Y, so mathematically we could solve. But to make our lives easy, I'm going to pick trials 3 and 1. And which one would I put on top? I would probably put trial 1 on top because it's got larger values. So I'm going to do my same setup, write a generic equation for the rate law for 1 and for 3, and then I plug in my values. And now notice we do know the exponent y is 2, but it doesn't matter because, and of course, because the concentrations of B were held constant between the two trials. And of course the K is still a constant, so it cancels out. And so we're left with 2 to the x equals 1. And if you go solve for the x there, you're going to find the natural log of 1 divided by the natural log of 2 is x. Well, the natural log of 1, you know, is 0. Just by the way, when we got right here, you could say, how could I possibly get 1 by raising 2 to some power? You would have to know that that had to be a 0 there, right? Because anything to the 0th power makes 1. That's the only way to get 1 with a power. Unless this had been 1. All right. So, x equals 0. What does that tell us? That tells us that the concentration of A does not affect the rate of reaction. Right? I mean, look at our data table. We held B constant, and we have twice as much of A in trial 1 as we do in trial 3 at the beginning, and yet the reaction runs exactly the same rate. So it's not sped up or slowed down by changing the concentration of A. So we've just experimentally determined that A is not in this rate law. If you wish, you could put A in there and put a 0 on it, say it's 0th order in A. By the way, reaction order just has to do with the exponent. If something's 0th order, it's got an exponent of 0. If it's second order, it's got an exponent of 2. If it's first order, it's got an exponent of 1. All right, so right now we figured out that the rate of reaction for this reaction depends only on B and not on A, but it depends on B to the second power. Okay, so what does that tell us about the reaction mechanism? It tells us that the left side, the reactant side of the slow step, is B plus B. And that would be like 2B, right? So we don't know anything about the right side of the slow step. We don't know about any of the other steps. All this method of initial rates did for us was help us figure out what's in the what are the reactants on the slow step in the mechanism for this reaction. Notice that that 2B doesn't correspond with the overall balanced equation. There was 2A plus 1B in the overall balanced equation, but that didn't help us figure out anything about the mechanism, the reaction mechanism for this reaction. Okay, so the left side of the slow step in this reaction is B plus B, or 2B. Okay, as far as overall reaction order, I just described to you that the reaction order has to do with the exponents. When you write up a rate law, you would put in your reactants and raise them to their powers according to the experimental data, and then just sum up their powers, sum up those exponents to get the overall reaction order. For instance, if the exponent on 1 had been 1, on A had been 1, and on B had been 2, then we'd be doing 1 plus 2 makes 3 for an overall reaction order. And we would say something like this: reaction is a third order reaction. But it turns out our reaction order with respect to A was 0, our reaction order with respect to B was 2, and adding them up we get an overall reaction order of 2. So this is a second order reaction overall. We still haven't found K, so how do we find K? Well, we can substitute into the rate law. We've determined the rate law, and we can use data from any trial, but I'm going to pick trial 1. And so I would be putting in what I know from trial 1. Oh, well, before I put it in, I'm sorry, I would rearrange to solve for K. So rearranging to solve for K, I would have to divide by the B squared on both sides, right? Okay, so now plugging in what we know. 0.955 molar per second was our rate of reaction in trial 1. And the concentration that affected that rate was the concentration of reagent B, and so it had to be squared, and so there we go. We're going to be able to solve for K. We'll get a number, but we need to talk about units here. The units on K are whatever they need to be so that the units on the rate come out in molarity per second. So what's constant here always is the rate is measured in molarity per second. So when you do the math here, you're going to get, this would be your answer to 4 sig figs. Here it would be to 3 sig figs. And this is actually, sorry, this is the value for K, but rounding it down to the 3 sig fig, or rounding it to the 3rd sig fig, would give me rate equals K times the concentration of B squared. So I should be able to take, if I want to predict what the rate of reaction would be for this reaction at this temperature, if you just tell me what the concentration is, I can tell you how fast it's going to run initially by putting in the concentration of B and squaring it and multiplying by the rate constant K. Now, I need to talk about these units again. I'm going to go back up. I want to show you that this was molarity per second, and this was molarity squared in the denominator. So if you did some cancellation, you'd find out that this molarity in the numerator would cancel out. You'd end up with a molarity in the denominator. And then you'd have seconds in the denominator as well. So that's why this ended up being molarity per molar per second. You would read this as 0.153 per molar per second.